Welcome everyone to this week's Autonomy Talks. This week is a great pleasure to have with us Dr. Mathias Hudoba de Badyn, who is a postdoctoral scholar at the Automatic Control Lab at the ETH Zurich, and also an incoming associate professor at the University of Oslo in the Department of Technology Systems. So something about Mathias. In 2014, he graduated from the University of British Columbia with a Bachelor of Science in combined honors in physics and mathematics. And then he moved to Seattle, where he obtained a Master of Science and a PhD from the University of Washington. His research interests include the analysis and control of networked dynamical systems, and today he's going to talk about network science in control from smart cities to a smart future. And I guess this is also will tell us about his plans for the next years as a PI. I'm personally very excited to hear more about this, and therefore I'll give you the stage. Mathias, go ahead.
All right, thank you, Joel. Thanks for everybody for being here. I know it's a really busy time in the summer. It's a great pleasure to be at this prestigious seminar. So I'll give a little bit of an extended background about myself, just to start off with. So I was born in Toronto in Canada, and then I moved to the middle of nowhere in Saskatoon, where I spent a good chunk of my childhood before moving over to Vancouver, where, as Joel said, I did my undergrad at UBC. Here I did what's called the UBC Science 1 program, which introduces undergrads to research. And so I followed that up with a stint at the Canadian Institute for Theoretical Astrophysics and then the Department of Physics in University of Alberta. And all of this led me to go do my PhD at the University of Washington. And now I'm a postdoc here at ETH in the Automatic Control Lab with John Liguros and Roy Smith. So the one slide snapshot of my work is I use network science to understand how you can take lots of different kinds of systems, connect them together, and get them to effectively coordinate. And this borrows a lot of tools from control, optimization, and game theory, which I'll get into throughout the next hour. When you look at network science in the context of control, there are maybe three fundamental questions that drive my research. So first is what role does the network play in control and estimation tasks? And how do you design or optimize these sorts of networks for control? If you have any sort of baseline way of designing these networks, then you can construct systems from the ground up that work well with each other. And then lastly, what's the interplay between learning and control from a network's perspective? This is a bit of a new hot topic, and I'll discuss this towards sort of the end of the presentation. But to give you some motivation about where the application interests of my work comes from, there's a global energy crisis. We're pumping out way too much CO2 into the atmosphere. This little blip here is from the lockdown during the pandemic, but aside from that, we can expect that this trend will continue at least into the near future. And if we look at where this CO2 and global greenhouse gas emissions in general come from, my PhD was actually in aerospace engineering. And if you look at the aviation sector, despite everyone saying don't fly to conferences and things like that, it's actually a very small portion of global greenhouse gas emissions. And this is maybe a sort of liberal estimate. The more conservative estimates I've seen go up to maybe about 4%. But the real kind of chunk of where greenhouse gas emissions come from is, surprisingly, at least to me when I first saw this, residential and commercial buildings. It's about 18%. And if you include the energy industry and transmission losses, sorry, Zoom is saying my mic just dropped out.
I missed just a word.
Okay, but can you hear me now?
Brief.
Okay.
Yeah.
Thanks. Okay, so if you look at, 18% comes from buildings, and specifically about 10% of that, so 10 out of 18% is from heating and cooling of buildings worldwide. And if you look at just some methods of addressing these challenges, there may be two kind of predominant philosophies on what we should do to lower the greenhouse gas emissions. One is to decarbonize the electric grid, swap out fossil fuel plants and switch them for renewables and maybe nuclear. But another thing that we can do, and this is maybe more natural for control, like controls and optimization people, is just minimize the amount of energy that our heating and cooling or energy systems are using. But I would argue that if you do large-scale control of infrastructure systems, then you can actually address both strategies simultaneously. And so this is where kind of the role of the network comes into play to address this challenge. So I'm going to start and build up a network from the ground up, and then you'll kind of see why the role of the network plays a large part in being able to control and these sorts of systems. So let's pretend you're living in an apartment building. That apartment building has some sort of physics. Like when you're trying to heat or cool your apartment, what you're doing is also heating or cooling like your neighbor's apartments. And likewise, what they're doing in their apartment affects you a little bit because there's some transmission through the walls. And so this forms sort of a physical network. Physical information is being exchanged from this heat transfer, and that forms, a network. And then you might have a bunch of buildings that are connected to maybe a district heating or district cooling grid, like here in Wallisellen and Dubendorf, there's a district heating grid. And these might be serviced by a bunch of heat pumps, maybe one heat pump per building, connected to some sort of water storage, all connected to a large scale district heating grid that's connected to, maybe the garbage incinerators, for example. And all of this is connected also to the electric grid, which is a massive network of itself, and other utility grids, potentially, natural gas or water grids, domestic water grids. And so all of this forms a giant network, and all of these systems share information, both physical information in the sense of what the dynamics of each of these agents is doing and affecting each other, but also algorithmic information. There's the potential to have these systems coordinate with each other using a common control algorithm. And so that begs the question, how do you deal with that network? Can you abuse or design that network in such a way to help you achieve these sort of control and optimization tasks? And so you need a new paradigm of control, which incorporates exactly this kind of network science. So how I think about networks from a very abstract perspective is that they're nodes coupled by interactions. These interactions can be cooperative or antagonistic. They can be excitatory or inhibitory. Each agent in this network, represented by a node, has its own self-dynamics, but also some coupling. So the dynamical process that happens on the network, or on each node in the network, is affected directly by some coupling between neighbors. And this introduces a lot of notions of control that are not necessarily classical. So, for example, the classical thing would be to just take one of these systems and inject some exogenous signal into it, control the system directly. But that signal can be used through physical and algorithmic connections to propagate across the network and influence nodes, not just the one that you're directly introducing the signal into. But you can do also combinatorial things. For example, you can create or break connections. And you can also modify node parameters by changing the dynamics potentially in this function F or this function G. You can change parameters in one node that will affect other nodes on the other side of the network. So the application focus here is smart buildings and infrastructure systems. So kind of the punchline of my work is that I allow distributed control, or I do distributed control that allows building and energy suppliers to do real-time energy minimization. And because we're doing clever things like model predictive control, we can show that in a live experiment, we can do about a 30% reduction in electricity usage. And this is validated on an experimental testbed that I'll discuss later in the talk, but this is the NEST building at EMPA, which is one of the Swiss national labs over in Dubendorf. And if you think about, reducing 30% of energy, and you think about this 18%, specifically the 10% of global greenhouse gas emissions that are directly coming from heating and cooling of buildings, and you reduce that by 30%, that's about a 3% reduction in global greenhouse gas emissions. And that's about twice the aviation sector. So that's a huge savings that are potentially possible through scaling up of these sorts of algorithms. Okay, so here's the key idea. Let's go back to this schematic of a infrastructure system. Here I've also included electric vehicles and charging, because that's going to take up a large part of electricity usage going forward, especially in countries like Norway, which have huge tax benefits and incredible uptake in electric vehicles. But yeah, so let's say each one of these systems here wants to do some control, but they want to do optimal control. They want to minimize the amount of energy they're using, subject to some operational constraints. So, for example, if you have a heater in your apartment, it might have a maximum power output of 200 watts, let's say. And then there's some equality constraints that take into account, let's say, the physics of the system. So the dynamics or energy balance. And through some clever algorithm, we might be able to get these systems to somehow coordinate by sharing information that I'm denoting here by P. We'll later see in this talk that this P is a dual variable coming from this optimization problem. So what you can do is say, all right, I want globally to solve the optimization problem of minimize energy across the entire city. But what you do in distributed control is you can split the optimization problem among the agents. Each one minimizes their own local cost, so maybe their own local electricity usage. But the problem is two agents might share a variable. So the energy requested by a consumer has to be equal to the energy supplied by a supplier. And so you need to devise some sort of iterative procedure that allows them to agree on that variable, and that variable being heat, which we'll see later is a dual variable for these sorts of optimization problems. So one prototypical way that you can get systems to agree on something, in this case, the optimization variable, it's an algorithm called consensus. And consensus does a lot of stuff. What it basically is, it's distributed averaging. Every agent has some state, X, and that state, they're going to each agent will modify that state by taking a weighted average, a continuous weighted average of the difference between their state and the state of their neighbors. And this node state can be a lot of things. For example, in aerospace applications, it can be a formation setter or heading. So pictured in the middle here, these are, for example, firefighting drones. I'm sure you've all seen in Canada, there's a ton of wildfires, especially where I grew up in Vancouver. There's an insane amount of smoke from up north. And when I was in Seattle, there was an insane amount of smoke coming from California. So autonomous firefighting is a thing that people are interested in. And one way to get them to coordinate with each other to, get the agents to agree on a common heading is to use this type of consensus algorithm. But you can do also, that's backwards. You can also do interesting things in spacecraft applications by getting satellites to, for example, if they're, for example, in a large baseline telescope, you have multiple satellites that all need to be pointed at the same object. You can use consensus to get them to agree on an attitude or some sort of inertial coordinate system. For this talk, however, we're going to focus on number 3 here, which is this sort of common optimization variable. So the thing I want you guys to get out of this talk is that consensus is an algorithm that is useful in practice, but it also demonstrates key features of network science in control. And so in this first part of the talk, I'm going to discuss how the role or how the structure of the network plays a role in control and how you can kind of optimize networks for control, maybe by choosing parameters well or choosing network structures in a clever way. And then I'm going to discuss a little bit of learning in the context of network science. And then I'm going to close the loop and show how we actually use all of these in practice in a distributed control setting, all focusing sort of on this experimental test bed. So first I'll discuss, first I'll talk about networks and how they play a role in sort of control applications. So in this part of the talk, I'm going to motivate the idea of a self-tuning network. So the idea here is if we have a network system and we're able to control some nodes in the network, what are the best nodes to inject signals into, and what are the best nodes to observe at each time step? And we're going to devise a procedure that allows us to include this as part of an optimal control problem. So this is the most technical part of the talk. We're going to introduce some of the algebraic objects that you use in graph theory and network science. So first of all, there's a graph. This denotes nodes and connections between the nodes. Each node is going to be assigned a state, and I'm going to have a set of possible actuator locations. This is a subset of the nodes that I can pick at each time step to introduce control inputs into. Then I'm going to have a set of possible sensor locations, which are nodes that I can detect the state from. And at each time step, there's going to be a set of active sensors and a set of active actuators. So actuators being S of t and sensors being T of t. And then from these active sensors and actuators, I'm going to have an input and output signal. So the inputs go into these actuators and the outputs come up from the sensors. And of course, the network itself is going to have some sort of dynamics, potentially depending on the set of active actuators. And so the goal here is to jointly adapt the active sensors and the active actuators alongside the control inputs in order to optimize some sort of objective. So I'm going to start with the most broad problem possible, and then narrow it down to an example in LQR where this kind of like abstract notation becomes a little bit more clear. So bear with me for a second. The easiest kind of general problem to set up is what we're going to call the cardinality constrained architecture design. Here, we're going to pick basically exactly K actuators at each time step and exactly L sensors at each time step. So the set of possible actuators is now combinatorial. It's the power set of the these possible actuator locations. But this allows us to write everything in a vector that has consistent size. And so now we can motivate the idea of having a history of trajectories, or not of trajectories, sorry, a history of outputs of common size and a history of inputs of common size, all coming from different nodes or different actuators. So then the problem of assigning optimal control becomes what we're going to call an architecture policy, which is a mapping from these histories to a set at the current time step of the actuator locations, the sensor locations, and the control inputs themselves that we're inputting into the actuators. And so then using this policy, we can then compute the optimal control and then update the system dynamics. So what we're going to do here is optimal control. So there's going to be, let's say, a minimization of an expected cost, where here we're denoting CT as being some stage cost depending on the state and the control, as well as a terminal cost at the finite time horizon length T. The policy is therefore just the minimization or the argmin of this cost. And the main theorem that we have from this is you can solve this with dynamic programming. So if you consider the optimal control problem, minimize this cost subject to dynamics, then the optimal cost function can be obtained from the dynamic programming recursion, where you write down the Bellman equations. So you start at the final time step, you go one time step back, and you solve for the cost to go. And from this, you can also, from these Bellman equations, you can also compute the optimal architecture policies as the argmin of these Bellman equations. And so that's the main result. You can solve this with dynamic programming. However, there's a bit of a caveat in that these argmin problems are combinatorial at each time step, and that'll become clear in this setting of LQR. So in the LQR case, you're minimizing a quadratic function in the state and a quadratic function in control, as well as a terminal cost at the final time step. The goal here actually is to select the actual control matrix. So if you condense this problem of picking, let's say, K nodes at each time step to control, then that corresponds to finding some sort of B matrix where each column in this B matrix is selecting the node that you're controlling. And so and then you have linear sort of time invariant dynamics, except this B matrix here is also a selection. It's a variable that you're selecting from a combinatorial set. Okay, so the main theorem here is that, again, you can solve this with dynamic programming. However, you can explicitly, in the sense of solving the LQR problem, you can explicitly find that the optimal cost to go are piecewise quadratic, and the optimal controls are piecewise linear. And these are defined over a finite partition of the state space. And I'll show an explicit picture of this, and it'll make sense then. But first, I want to show you what these the cost to go functions look like. So explicitly, you can compute the control, and the control depends on your choice of the control matrix B, which again denotes which nodes you're inputting signals into. And if you do the standard quadratic ansatz to solve for the Bellman equations, you get something that looks like a Riccati equation, except now you have to do a combinatorial search over all possible B matrices. So all possible matrices that where the columns correspond to different nodes. And so this is combinatorial. And I'll address that in a second. But first, I want to show you the effect of choosing this infimum over this all these possible matrices. So this is an example for 4 time steps using a 2x2 system. And the possible controllers here are either control node 1 or control node 2. And this piecewise quadratic cost to go function is plotted in these 4 plots here. And basically what it says, if you're in the purple region, you control node 1. And if you're in the blue region, you control node 2. However, within each colored region, the function is quadratic. However, as soon as you cross over into the different regions, then you control a different node. And so that's the notion of why this is piecewise quadratic. Okay, so to address the combinatorial complexity in finding the optimal actuator, there's a greedy algorithm. So at each time step, what you do is you pick the nodes one at a time. So at each time step t, what I'm going to do is start with an empty control set. So an empty set of active actuators. And then for each possible actuator, so at this time step, there's going to be, let's say, I don't know, some number greater than k, let's say k star, possible actuators. And I'm going to check each one of them. And then I'm going to find the one that gives me the smallest cost to go. And I'm going to add that into the actuator set. So this means that I'm going to add a column into the B matrix corresponding to the node that minimizes the cost to go. And I add that to the actuator set, and then I update the B matrix with this column. And then I repeat this, and I terminate once B has exactly k columns. And so this is a much simpler search time. It's not combinatorial. And just to give you an idea of the sort of performance improvements that you get, first I'm going to compare the brute force case where for a set of, let's say, 40 nodes, a network with 40 nodes, I compare the brute force search to the problem where I'm fixing the optimal nodes to control at one time step and using those for the remainder of the time horizon. So I'm going to call that the fixed architecture. So the blue curve here again is I pick the best nodes to control at time step 1 and use those for the remainder of the time. And then the red here is where I'm at each time step computing the optimal set of actuators. And you get a massive performance improvement. And this is actually pretty typical. This is for a completely random setup. But if you run random setups, this is actually exactly the kind of performance improvements that you see. So next, I'm going to compare that to this greedy policy. And so here, I'm just going to do it on a 2x2 system because I want to get a histogram in a reasonable amount of time. So I'm comparing the dynamic programming solution, which is the brute force combinatorial search over a time horizon of 5 versus this fixed policy, which is in red. So the fixed policy performs the worst. And the greedy policy works actually quite well, but it doesn't come close to the dynamic programming, the brute force search. However, the greedy policy will always outperform the fixed policy because at the first time step, they'll pick the same actuators. And then the greedy policy will then therefore thereafter continue to update the actuators in order to get you even better cost reductions. Okay, so to conclude with this section, a paradigm for self-tuning network control architectures was proposed, and we showed that you can solve this with dynamic programming in a very classical sense. And when you look at LQR, you can show that you have explicit solutions, which are piecewise quadratic in the value functions, and then piecewise linear in the control actions. So this is one kind of a way that we can introduce the role of having a network in a control system. But now I want to turn our attention to the idea of optimizing networks for control from an algorithmic point of view. So the idea here is looking at consensus. I had sort of these highlighted parameters here. UI is a control signal, so we know how to optimize control inputs. However, I have these two parameters here, epsilon and W. So epsilon here is a time scale. This tells us how fast a node is integrating information from its neighbors in a holistic setting. And this is set by physics. So for example, ground robots will often have a slower time scale than drones, which operate on much faster time scales. However, Wij is an algorithmic choice. This is how much agent I trusts agent J, or the information from agent J. So a larger W means you're going to accept information faster from agent J. However, we can think about what are the best choices for the timescales and the best choices for these edge weights, Wij. And so that's what I'm going to propose in this section of the talk. And to motivate this, like imagine you have this infrastructure system where everyone is doing some optimal control and they're passing information to each other. You might have some sort of antagonist that wants to corrupt the information that's being transferred between agents. Some sort of cyber attack. And so to model this, I'm going to take the linear systems that inhabit these sort of systems, and I'm going to write down their transfer function. And W here is going to represent some sort of antagonistic input into the signal. And there may be two classical ways of looking at how antagonistic inputs affect linear systems, and they're the H2 and H infinity norms. So H2 norm will measure the steady state covariance under a Gaussian, unit Gaussian white noise input. Equivalently, it's the impulse response of the system, or measures the energy of the impulse response of a system. The H infinity norm, on the other hand, will measure the worst case response to a finite energy signal. And so you can ask the question, what are the best edge weights and what are the best timescales for H2 and H infinity performance? And so the goal here is to design and solve tractable optimization problems, focusing on network science as a tool. And so I've done pretty much every permutation of this problem, like how weights affect H2, how timescales affect H infinity, et cetera. But the goal of this section of the talk is just going to focus on how the edge weights affect the H2 norm. So for this, I'm going to go back to our consensus algorithm. And here I'm going to specifically look at what's called leader-follower consensus. So in leader-follower consensus, you take the graph Laplacian, which is the state matrix for the dynamics of consensus, and you identify some nodes. Here they're labeled in blue, that are called the leaders. The leaders, you're going to pretend that they're a control input. You control the state of the leaders, like for example, in this drone swarm with a joystick. And then what you do is you take the graph Laplacian, you partition out the leaders, which I've denoted here as LR, and then you look at the dynamics of the followers. For example, the nodes in red here. And so if you write down the dynamics of this, you get a slightly modified version of consensus where you have additional terms here coming from the connections from the followers to the leaders. So these are extra edges, if you will. And the important thing is you can write down the H2 norm explicitly of these dynamics because this matrix, if the graph is connected, is always invertible. So you can write down explicitly the H2 norm, so which is this guy here, the trace of B transpose times the inverse of the state matrix times B. B is a matrix here that just tells you which nodes are connected to which leaders. So I can write down min this subject to maybe some bounds on the edge weights. Specifically, all the edge weights should remain positive if they're an edge, because we don't want to disconnect the graph. And if I look at a network here, a very simple one, the nodes here in red are the leaders, the nodes in beige are the followers that are connected to leaders, and then blue are just followers. I can solve this problem in an interesting way. I can pretend that this network here is an electrical network. If the edge weights are all now conductances of resistors, I can explicitly write down the H2 norm in terms of the effective resistance of this pretend resistor network. In particular, it's the sum of effective resistances from the source nodes here in beige to the leaders. So if I literally just make this network on a breadboard and I stick a probe at one of the beige nodes and then stick another probe at the leaders, which I've grounded and set to 0 voltage, whatever and then there's a 1 amp current between the leaders and the source nodes. If I stick probes at the source nodes and the leaders, I'm going to measure the effective resistance of the source node to the leader. The H2 norm is simply the sum of all of those effective resistances. And so if I say want to, for example, solve this problem with gradient descent, through this electrical interpretation, I can write down the gradient of this H2 norm in terms of a sum of a bunch of voltages across the graph. And so if I turn my attention to networks that are constructed through series and parallel additions of resistors, then I can actually compute these voltages very quickly using what I'm calling a decomposition tree. So let's say I have a graph here, G1, and I have this tree where all of the leaves of the tree are individual resistors, and then the parent nodes of are whether or not I add those in series or add those in parallel. So if I add these two elements in series and then add those in parallel and then add it in series again, I get this graph, G1. And similarly for this graph, G2, I would get something that looks, I would get a decomposition tree that looks like this. I showed that the H2 norm can, first of all, be computed using these decomposition trees, meaning that the H2 norm itself has some addition formulas that resemble the series and parallel addition formulas for resistances. But I also devised an algorithm that allows you to use this decomposition tree that computes the relevant voltages for the gradient descent using just electrical operations. And you can compute this in much faster time than the standard linear program for the H2 norm minimization. And there's also a completely equivalent theory of matrix weighted graphs, if you will. So you can have matrix valued resistance, matrix valued voltage, power in this weird matrix valued graph becomes something called an infimal convolution of, and it's a beautiful theory, and everything pans out. Like you can do all of this kind of electrical formula stuff to optimize for matrix weighted graphs as well. But that's an aside here. If you want to read the papers, they're here. So what I want you to get out of this is that you can optimize these weights, timescales and edge weights for consensus in order to maximize your network resilience to antagonistic signals. And there's a very interesting theory that you build upon in order to do this. Okay, so now I'm going to switch gears and talk about machine learning in the context of network science and control. So what is the role of learning in control systems? We're all familiar with this very basic block diagram. We have a plant G. That plant might correspond to, for example, the building that I'm going to run experiments on. The problem is every building is individual. If you want to run an algorithm on a specific building, you need to model it using an expensive engineering process. However, the idea is that machine learning might be able to automate this to some extent. And so the idea is you have some data, let's say some input-output trajectories of a linear system, and you want to learn the dynamics of the model. There are many paradigms for this in control and in computer science. In my view, there's two paradigms. There's the classical one, which are things like system identification, the modern iterations of this being data-driven control from the Willems lemma. And then there's AI methods that involve things like artificial neural networks or reinforcement learning. And there are different pros and cons for these. And the trade-off that you have is between generalizability and certifiability. So generalizability I'm going to define as the scope of the systems you can model. And certifiability is going to be things like what control people care about, like system theoretic guarantees, robustness, stability, and things like that. So with the classical one, you obviously get tractable certificates because we build control algorithms in order to have them from the ground up. But the con is that these are not generalizable. Like you have strict assumptions on, this is a linear time invariant system, or it's difficult even to do these things for general nonlinear systems. However, with AI and ML, you have very high generalizability. You can, for example, come up with a model of how I respond to a cat picture, which is in order to drive, I don't know, some sort of ad revenue model or something. And that's a very difficult nonlinear model to come up with. But the con is you have completely intractable certificates, at least for now. And I think in the future, this is kind of going to drive the area of research going forward, is coming up with these highly generalizable models and then coming up with tractable certificates so that you can actually use them in a control system. So we've seen in the last section that you can modify network parameters, and that yields some performance improvements in the context of control. So in spirit, can you come up with a similar procedure for neural networks, but something that control theory people care about? So here's a artificial neural network. We can pose this question as a design problem for the network topology. How do you decide upon the actual topology of the hidden layers, as well as the node parameters, which in this case are not scalars like we saw or scalars or vectors or matrices that we saw in the consensus thing, but they're now functions. We have to choose the functions cleverly in order to get something that control theorists care about. So in the context of this, I'm going to look for models specifically for buildings in order to be able to use model predictive control. So this audience is no stranger to model predictive control, so I'll skip through this. But I mean, the reason why you would use MPC for building control is because you need to incorporate weather forecasts. That is really the driver of how you're able to minimize energy consumption of buildings, is you can kind of abuse the energy that's already outside. But anyway, so MPC, you have a cost function. At each time step, you forecast into the future what your cost is going to be for a certain control action. Then you minimize it, but you need a model, which I'm going to denote here by xt as f of x, u and the disturbance d, which here is the weather. And then you solve this, you apply the first control input, and you repeat it. The problem is, if you want to solve this using standard convex optimization techniques, then this function f of x of t, u, and d that you're learning with the neural network has to be convex itself over the entire time horizon. And so this is a bit of a problem. There was a paper by Amos et al. In 2017 that talked about designing neural networks that guarantee convexity, but this was for a single time step. So using this neural network, the problem is you want to be able to compose the neural network with itself. Like xk plus 2 is going to be f of xk. So in order to have a time horizon of more than one time step, you need to be able to compose the neural network map with itself. The problem is that if you use this, it's not convex, and so you can't really use it in MPC with convex solvers. So our solution was to modify the network topology and node functions in order to guarantee convexity. So you pick the hidden layers in such a way, and you pick the way the data flows through the network in such a way, and then you pick the node functions themselves in such a way in the hidden layers using kind of your standard Boyd composition rules for guaranteeing convexity. And through that, we're able to design a neural network that is composable with itself and maintains convexity. So the trick here is that you need to choose the functions in the hidden layers, which are now stacked in these big black boxes here. And you need to choose this function g in order to be convex. And so the theorem is that basically the functions need to be either positive, depending on where they are in the hidden layers, or convex and non-decreasing. And then the edge weights, of course, all have to be positive. And then you can show that the composition of this neural network with itself is in fact convex in the the state and input parameters, or the state and input variables. Okay, so once we have this, how does it perform in an actual building control experiment? So now I'm going to talk about the actual setup here. So this, of course, is with EMPA, the national lab I mentioned in Dubendorf. There's this building here called NEST, which is known as a quote unquote vertical neighborhood. It's a shrunken down version of what you would see in an actual like neighborhood in terms of infrastructure. So it has a district heating grid and a bunch of energy conversion and storage machinery that you would normally see at a larger scale, all shrunk down and completely accessible to anyone that wants to run experiments on it. So in particular, we're going to look at this unit here called UMAR. UMAR is nice because it has 2 bedrooms that you can control individually as well as a living room, but the bedrooms are roughly symmetric. So you can have one controller in one bedroom, another controller in another bedroom, and compare them side by side. And so that's what we do here. In one bedroom, we stick in an RMAX model, which is like a classical system identification technique for finding a linear system from input-output data. And then we put one of these input convex neural networks in the other bedroom. And so the bedrooms, while they're symmetric across the living room, they have different exposures to the sunlight and the ambient temperatures. So you're not going to see the exact same thing in both bedrooms, but you see something very representative. So basically, this is just a validation that these 2 techniques perform similarly. In experiments, you always have things that go wrong. So in this shaded box number 2, we have a storm that blows open the shutters in the windows. And so the sunlight goes in, and then you have both controllers operating at max control input, but they're not able to cool down between these temperature bounds. So then if you look at how MPC overall performs, not just with these input convex neural networks, but using different types of models, you can see that in these plots, I'm plotting in blue here the kind of standard operation, which is a hysteresis rule-based controller in blue, and then in orange is every dot here is 1 day of operation of MPC or this rule-based controller. The units here are called cooling degree solar days. So this, roughly speaking, what this means is a cooling degree solar day of 0 means that you would expect to have 20 degrees in your room. You would not need to apply any energy. That's the unit here. And so basically what you get from these plots is that MPC overall, regardless of what model you're using compared to the rule-based controller, requires 33% less cooling energy at 5 cooling degree solar days and 28% less at 15 cooling degree solar days. So that's where we get this roughly 30% less energy than standard operation. And I should point out that the standard operation is about as highly tuned hysteresis as you can get. Like, this was done by an engineering firm. It's very representative of a top of the line building management system that you would purchase and install in an apartment building. So this is really the kind of best comparison you can get. Okay, so now I'm going to kind of close the loop here and discuss distributed control, and then wrap up with what I'm going to motivate as a suboptimal distributed control. So we've seen in this setup here that, you know, we might have an apartment building that we're controlling individually, but it's hooked up to something like a district heating grid. And I'm going to want to minimize the energy of that district heating grid, as well in conjunction with the minimizing the energy of the individual apartment units. And so this requires distributed control. And the kind of questions that you want to ask when you're doing distributed control is, you know, what happens if you add new agents to the network? You build new buildings and you connect them to, you know, the utility grids that you're using. Does your algorithm handle that? Do you sacrifice performance as the network gets larger? And can you even design these algorithms from scratch, let's say? And the answer is yes, you can, but modularity and scalability are definitely challenges. So I'm going to go back to this idea of building MPC. But now I'm going to consider an infrastructure network. So we're going to ignore the electrical grid, but we're going to look at a collection of energy suppliers, some building units that we can control, and some building units that we can't control. And each one of these agents has different objectives. So the supplier wants to minimize the electricity cost. The consumer wants to minimize the utility cost, which isn't necessarily the same thing as the electricity. The electrical grid might care about things like balancing supply and demand, frequency regulation, et cetera. But for the purposes of this talk, we're going to ignore that. So if I write down the global MPC problem of controlling this entire system, it looks kind of like this. The S here stands for supplier, C stands for consumer. I want to minimize the electricity cost of both, subject to the physical constraints and the operational constraints. So what I can do here is separate the problem among the agents. Each will minimize their own cost. However, agents will share variables. So in particular, the energy requested by the consumer is going to have to be matched by the energy supplied by the supplier. And so we're going to devise some sort of iterative procedure that allows them to agree on that variable. You know, one of those things being consensus, as I motivated in the first part of this talk. And so what they basically do is they share dual variables with each other in order to iterate on them until they reach the sort of energy balance equation. Or they agree on how much energy has to be supplied by supplier and consumed by the consumer. Okay, so without going into the details of the distributed control, I'll just show you how it works in practice. So here, what I'm doing is I have two apartment buildings, two apartment units. There's Umar, and then there's another one called DFAB, which is a cool building that was, or a cool part of the building that was digitally fabricated using 3D printers extruding concrete. But for the supplier, I'm going to consider the local district heating grid inside of NEST, which has a heat pump and a hot water storage attached to it. And that's going to be our supplier. What I'll show you here is basically that the algorithm works in practice. It controls all the room temperatures in DFAB. There's 7 rooms in particular. The one thing that is not so great about running experiments on DFAB is that the temperature sensors have basically a 1 degree resolution, which is a little bit unfortunate. But what we can see here is that MPC is able to kind of keep the room temperatures in between the bounds, as well as the temperature of the hot water tank that's supplying the rooms. Okay. So the next question is, in simulation, what happens when new agents are added to this network? So what happens if you compare this distributed approach to the centralized approach is that the distributed approach basically doesn't grow in complexity as you add more agents. However, of course, the centralized problem grows very quickly in terms of computational time. So it scales well, let's say, in terms of the number of nodes. However, it doesn't scale well with the number of edges. So basically the number of apartments communicating with suppliers. So what I've plotted here are different lines for different ratios of suppliers and consumers. So the blue line here is 1 supplier for 1 consumer. The red line here is 1 supplier for 5 consumers. And yellow here is 1 supplier for 10 consumers. This just means that there's a higher density of edge number of nodes. And so basically, this does not scale well if you need to communicate more. And so this motivates the idea of, can you limit the computation without sacrificing performance? And so this idea is basically, instead of solving the distributed MPC problem to completion, which requires multiple rounds of communication per time step, you can instead limit the number of iterations, and then through some mathematics show that the algorithm will maintain properties that we care about, for example, stability of the algorithm. And I'm running a little bit out of time, so I'm just going to go through this at sort of a high level. But the idea here is we have some sort of distributed MPC problem here, where we're just going to take quadratic costs for each agent. we have some local dynamics and local constraints, as well as some coupled constraints. And I've just written them here in some sort of polytopic form. And these local dynamics and constraints here are the top constraint, and then we have some coupling across all the agents. And so through this, if we solve this in a sort of semi-decentralized way, you can also solve this in a purely distributed way, but the algorithm on the left looks a lot more complicated. The idea here is if you use a dual ascent method, in this case, a forward-backward method, if you regularize the dual problem with some parameter epsilon times the dual variable, you can separate the system into two bits: the physical system, or the plant that we're trying to control, and then a subsystem corresponding to the algorithm, which is exactly solving the optimization problem with an accelerated forward-backward method. And what we can show is that under this scheme here, the plant subsystem is locally input to state stable. And then we can show that the actual algorithm itself is also input to state stable, with a clever choice of parameters. And then depending on how you choose the parameters, basically the number of communication rounds and epsilon, how much you're regularizing the dual, then you can show that in a finite number of iterations, the closed loop system is locally input to state stable with respect to any disturbance entering the system, in this case, the weather. And you can also derive some bounds in the disturbance-free case on how close you are to the optimal solution. And so you can address this challenge of modularity and scalability in terms of the number of agents, specifically for this case of distributed control. Okay, and with that, I think I'm running out of time. So just to summarize the talk here, I've discussed how networks operate in control, how you can optimize networks for good control, then how learning, you can approach learning from the perspective of fundamental network science, and then you can close the loop and apply all of these together to do interesting control tasks that we then validated in experiments with live hardware in buildings and supply chains, or in infrastructure networks. And with that, I'd like to thank you for your attention and open the floor for questions.
Thank you very much, Mathias, for the very interesting talk. Let's open the stage for questions. You can either write your question in the chat or simply raise your hand and ask directly. So maybe I'll be the icebreaker. By the way, Emilio apologizes, but he had to leave for another meeting, I guess.
No problem.
So my question was, you probably already thought about that, but in this talk, you approach the operation of these control systems, right? But do some of your studies highlight some interesting things when one comes to designing the system? So can you, due to the fact, or due to your discoveries, can you inform better design policies for buildings in this case?
Yeah, absolutely. So there's this idea of constructing networks from the ground up. For example, you can think about, okay, how am I going to design a district heating grid if I'm going to start a city from scratch? And these are absolutely questions that you can address with network science, as well as even being informed by the design of a control system as a co-design problem at the same time as designing like a district heating grid. I didn't really talk about this in the section on the optimization of networks, but this idea of series parallel networks is a way to construct networks from scratch that, for example, will give you good H2 performance with consensus. So if you plan on doing some sort of consensus algorithm for different nodes in a network, you can get exact H2 guarantees by constructing networks in the series parallel way. And I should note on that point, it seems weird to construct networks from series and parallel operations, but it's actually a very large class of networks. From a graph theory point of view, there's a delineation between series parallel networks and non-series parallel networks. And the delineation is if you have a complete graph on 4 nodes. So if you're familiar in electrical engineering of the Wheatstone bridge, if you have that kind of structure in your network, then it's not series parallel. And all networks that do not have this are series parallel. So it's actually a very broad class of networks, and in certain settings, it would make perfect sense to construct your networks so they are series parallel. For example, in electric grids, having Wheatstone bridges in electric grids is usually bad. So yeah, absolutely. You can definitely design systems using network science principles, specifically from both the control perspective and just the co-design problem.
That would be very, very cool. I mean, because I imagine also people designing buildings use tools that are totally different from the advanced ones you're working on to actually simulate the different performances, right? So it would be cool to embed these tools in their architectural process.
Mm-hmm.
So there is a question in the chat from Ariant. Could you elaborate on the epsilon parameter on the system dynamics, and what insight did you gain from your experiments on optimizing it against the H2 and the H infinity?
So the epsilon parameter, sorry, in which section? The optimization for like the consensus bits?
On the system dynamics, it says on the system dynamics.
So I'm guessing that's, let's go back to slide 40. Nope.
Maybe Ariant, if you can clarify.
The timescale parameter, I guess.
Mm-hmm.
Yeah, so the timescale parameter, let me just get to it.
Okay, yeah, it confirms the timescale parameter.
Okay, yeah, here we go. So yeah, so the timescale here, it's interesting. So you might ask the question, why not just divide through the dynamics by the timescale and then just solve for the bulk model? But it turns out that that's a bad idea because the epsilon is usually limited by physics. So like I mentioned in the talk, fast dynamics or drones might, for example, correspond to fast dynamics, and ground vehicles might correspond to slow dynamics. But if you look at the H2 problem for solving the timescales, it's actually, there's a separation principle. You can, if you write down the H2 norm in terms of this entire set of dynamics with the timescales and weights in them, then you can optimize them independently. And the insight that you get actually is that nodes to minimize the H2 norm, nodes that have lots of connections should be slow. And that's the insight you get. It turns out that the optimal timescale depends purely on local information. It only depends on how many agents agent I is connected to, the optimal timescale for H2 for the H2 norm. And so that's a very interesting kind of insight, because it's saying that and it makes sense, right? It's saying that networks will not transmit information if the nodes that have high degree, meaning the number of connections, are slow. They're like the central hubs of the network. And so if those nodes are slow, then antagonistic noise will not travel through them as much, if that makes sense.
Okay, and follows up, almost like normalizing for the number of connections or incoming volume of information. Is this also a security feature in some way, maybe?
Yeah, absolutely. That's one way of interpreting it. And that's actually exactly what you do. The optimal timescale is related to almost normalizing by, I think, the square root or the cubic root of the number of connections.
Great. Apologies, Ariant. I don't know why you cannot unmute yourself, but I hope I reported your questions nicely. Any other question from the audience? I guess you were a bit rushed in the end, but do you want to comment quickly on the outlook? What are the next challenges for you, Mathias?
Yeah, so the next challenges for me are, so I've come up with these sort of design problems for the basic algorithm of consensus, but I'm treating consensus as a dynamical system on its own. But usually consensus is embedded in a much larger scheme, right? It's for example, for example, agreeing on a dual variable when you're doing model predictive control. So what I want to study in the future is if you embed this with dynamics or algorithms on top of it, are there similar design procedures that you can do? Can you design good timescales, good edge weights, or good network structures for distributed MPC or distributed feedback optimization? And specifically, if you can relate it to algebraic structures like the graph Laplacian, because as soon as you can do that, then you can use tools from algebraic graph theory to study larger classes of algorithms. So that's the challenge that I'm going to be looking at over the next couple of years.
Very cool. Thank you very much, Mathias, and thank you everybody for participating. I think if you want to reach out to Mathias for deeper questions, you can find easily his email. It was on one slide, but also it's pretty easy to find him.
Yeah.
Again, thank you everybody, and thank you, Mathias. Good luck for the next steps.
Yeah, thank you, Joel, for inviting me to the seminar, and thanks everybody for taking your time to come.
My pleasure, and see you everybody next week for the next talk.